Are you going to share your screen or?
Yeah, give me a second. Can you guys see my R Studio? Is it large enough?
Yes.
Okay, and can you all hear me all right?
Yes.
Awesome. So today, for this session of Intro to R, we're going to be covering data types, data structures, and objects in R, which, if you've used R at all, you know they're probably the main source of your pains, as programming languages have very defined ways to deal with their inputs and outputs, and if you don't meet these requirements, we can get into trouble. To better explain this, I think the first key thing to remember is that R has 6 basic data types, which are character. This can be, for instance, letters or numbers enclosed by the double quotes. We have integer, which will be, as the name suggests, integers. We have, I'm getting there, I'm sorry, English is failing me. We have numeric, which is numbers that can have decimals, or they can be real numbers. We have logical, and this is only false or true. And we have 2 more. I think only 1 more. It's only complex, right? Everybody?
What about factors?
I cannot hear you. The notes mention 6 basic data types, but I'm pretty sure there's only 5.
I think, yeah, like for like basic stuff before you start putting them together, which is more like a vector. Yeah, it's like the base types, like just a single element. There's only like 5 or 6, I think. Yeah, complex might be like the number I and stuff.
Yeah,
that might be the complex one. Yeah.
So for now, we'll stick to the 5. And these data types are stored into a number of objects or data structures. And the first one, the main underlying one, is known as an atomic vector. And the important thing about atomic vectors is that they can contain only 1 data type per vector. So if we want to make, and there's a number of ways in which we can make these vectors. For instance, you can make an empty vector just by typing the common vector. And in this case, it produces a logical vector with nothing inside it. Or we can produce a vector containing characters and give it a length of 5. And that, as you can see at the bottom, produced a vector with 5 elements, but as we did not provide an input for the vector, there's nothing within. Alternatively, we can produce vectors with a sequence. Let me wonder if I'm doing this right. No. So and a very key thing to troubleshoot what's going wrong with your code and why your data types might be wrong is knowing that you can inspect these vectors in a number of ways. For instance, you can look at their length. So I've assigned my vector that I produce with the command C that produces a sequence from 1 to 5 to the object X. And I can now investigate it to better understand what its structure is in case something is not working. For instance, I can ask what its length is, and it's telling me that it's of length 5. I can also ask its class to understand whether my data type inside my vector is as I'm expecting. And here it's telling me that it's an integer vector, as we have only numbers from 1 to 5. If I were to produce a vector instead with characters inside, like Kevin and Lorenzo, and I were to ask once again what its class is, it will tell me that it's a character. Alternatively, to remind us of the few data types existing, you could produce a logical vector with a combination of trues and false, or a vector with decimal numbers. An important thing of vector that I briefly mentioned at the start is that you cannot include different data types within the one vector. And what R will do will be to coerce your data to all be of one data type. What do I mean by this? Let's imagine I'm trying to produce a vector with some numbers like 1 and 10 and some characters. Once again, characters are usually delineated by these double or single quotes. And if I do this and then I look at what my vector look like at the bottom, you can see that now all my 3 elements within the vector have the double quotes around them. And if I ask what the class of this vector is, it will tell me that it's character. And that's because when I provided the elements for this vector, there was one character, and for R, the simplest way to coerce all of these to be of the same data type was to interpret these 2 numbers, which I initially intended as integers, to characters as well. And this step that R does is known as coercion. And we can do this more implicitly when we want to convert our data from one data type to another. For instance, say we had this vector X that once again has the numbers from 1 to 5. But in this case, 1 to 5 might represent our 5 plots or some categorical variable that we do not want to interpret as a number. We can coerce it with functions like as character to convert our vector from a integer vector to a character vector. So if I now run as character and inspect the class of Y, it will show me that is now character and not integer anymore. And if we look at it, we can see that all the numbers within now have double quotes around them, indicating that they are being interpreted as characters. So these are just some of the functions that we can use to explore vectors. We have length, for instance, that tells us how long our vector is. We have class that tells us what the data type within that vector is. And we have structure. For instance, if I were to look at the structure of Y, it will give me a bit more information combined. So it tells me both that is a character vector, with 5 elements, and it then depicts these elements. And something like structures particularly is sometimes more relevant for some of the other data structures that we'll explore later. And when I talk about data structure, wait, before we jump to that, just another action that you can do with vectors, which will be probably very relevant in your work, in anyone's work, is to add elements to these vectors. And you can do this by the same function C that we used before to create a vector. So for instance, if I want to add, at the moment we know that y is from 1 to 5. Let's say I want to add a 6 to it. I can have C, y, which refers to my current vector, and then 6 as a character, because at the moment all of my elements are characters. And if I explore Z now, we can see that it appended 6 to the end of it. And vectors, importantly, can also support missing data, which in R is usually coded as an A. So say, for instance, I do not have information for the 7th element in my list called Z at the moment. I do have missing data for it. I can append in that position the just the NA, which you can see gets highlighted in a different color, highlighting that that's a special character. And if I then look at my Z vector here at the bottom, we can see that we do not have a value for the last element, is coded as NA. And there's a few more special values that we can use in R, and these include, for instance, inf for infinite, typed as in this way, or NaN, which means not a number. And that's to handle cases like when we're dividing 0 with 0, that we know does not result in, it's not a possible operation, does not result in a number. And so R returns this NaN. And I think it's very important to be able to screen for these peculiar data types, as they can be at the basis, for instance, as the error you've been struggling with for the last 10 days. For instance, recently I was helping a student in our lab with a project, and she will apply the same script that we use for a number of days before to an updated data set, and it will break. And it turns out after 5 days of struggling that one of the objects was not being read properly, it was being interpreted as NA, and our code did not handle NA. So how do we find special characters like NA? Well, there's ad hoc function that can help you with this. For instance, is NA can let you know at which position in your vector. In this case, you have an NA. And we can see that our vector Z has an NA in the 7th position, and is NA will return a logical vector telling us at which position we have an NA, and here it's telling us that at position 7 we have an NA. And this can be helpful, for instance, to identify possible issues, or even to include in your code for handling of errors and troubleshooting. Now, before I continue, can you all just confirm that you're still hearing me and seeing me fine? Because sometimes the quiet background can be misleading. I see I have 6 messages in the Zoom chat. Okay, there's request for calling the object cool kids. Sorry, I just saw it. I'll implement. And factor might be the 6th type of element. Okay, that's probably something to look at. So we covered how we can only have one data type inside the vector, but how we can include missing data and so on. So now let's expand a bit on, I think we covered these. Yes. Okay. Let's expand a bit on our vectors and look at the data structure that's very similar to vector, and that is a matrix. To produce a matrix, we can simply use the function matrix. I'm going to use the notation that we used before to give it numbers from 1 to 6 in step 1. If you're unfamiliar with it, just know that this is something you can do in R to produce a sequence. For instance, at the bottom, if I just type 1 to 6, you can see it returns this value. Sorry, I did not cover it well before. So we can produce a matrix with the values from 1 to 6, and I want these into columns. So I tell it to do n call equals 2. And if I run this, we can see that we have a matrix with 2 columns. And importantly, metrics are filled column-wise. So the first 3 numbers went in the 3 column across 3 rows. And afterwards, it covered the 2nd column. And we can call our metric cool kids with a Z at the end because we're a bit edgy. And now we can, once again, like we did for vector, we can inspect this metric in a number, these metrics in a number of ways to better understand it. For instance, we might ask for the structure of our cool kids matrix. And it reports here a number of details about this matrix. The first one, int, is short for integer, which points out why matrices and vectors are similar, and that because matrices are basically multi-dimensional vectors, in this case, or integers. So if we can then once again use the class function to see what class our data structure is, and in this case, it tells us it is a matrix. We can ask it how many rows there are in this matrix. We cannot. We can ask it the dimensions. Oh, sorry, I realized why. We can ask how many rows there are and how many columns there are with the n row and n call function respectively, or ask for the dimension all at once. Now, what I meant to say before, class tells us that this is a matrix. But what if we use instead type of, another function used to inspect your objects and better understand structure? We can see that this states only integer. And to be fair with you, I discovered this today. So if anybody in the audience has a better explanation regarding the difference between these two that can help us all better understand matrices, that would be awesome. Anyone?
Yeah, I think it's like basically just classes about like the kind of the size of the matrix, like the 2D or 3D dimensions of whatever it is. So if it's a matrix or an array, it's got like some n by m dimensions, whereas the type of is just getting the individual like one cell out of it. What is that like type of object? So it's like an integer if you filled it with integers, I think. But in this case, because it's cool kids, it's odd that it is doing type of. Yeah, I'm not sure why it's returning that, but type of is usually what I tend to use actually is just is instead. Like that's what I like the best. Like if you just type is on something, that's my favorite one to use.
Okay. Yeah. See how that can be.
Things can have many different classes at the same time as well, which is extra confusing. It's just kind of like a label to what it is, but yeah.
It looks like type is just a data type, right? Just the data type of the data within the matrix.
I'm just surprised because CoolKids is that our names in it, or what is it inside of CoolKids right now?
No, it's
numeric
oh, okay. Sorry, I thought it was character
the
string.
matrix from 1 to
Oh,
6.
okay, yeah.
It,
So in that
makes
case,
sense.
yeah,
I
it's
think
just point of
Jacob
the
is correct. It's telling us the data type within the data structure.
Yeah. So anyway, just pick one that you like and use it religiously. I use is.
So I think that's it for me for matrices. The next data structure that we'll be looking at is lists. And once again, we can make an empty list with list. We can make an empty list with a determined length. Let's see if I remember this. Mode equal list, length equal 5, and this returns as a list with 5 null elements within. This can be really helpful in for loops. For instance, you might make a list at the start of your for loop and then fill it iteratively. How would you fill a list though? You need to know how to access the individual elements with it. So before we do that, let's make a list with actually something in it. And list, the cool thing about list is that this word containers, list as containers, mean that they can contain a whole bunch of different data types, unlike vectors. So in this one, I might put an one, 1 plus 0.2, and a complex number like for I. And I'm gonna call it cooler kids, because lists are better than matrices. And if I now look at my cooler kids list, you can see that I've got 4 elements in my list with different classes. How can I identify the class of each of these elements? That's by accessing. First of all, I need to be able to retrieve them. And you can see here that we have a double square bracket 1. So if I want to access only the A, for instance, I'll have the double square bracket 1, and it will return only the A. If I want to retrieve the last one, use 4, and I have a complex number return. And then I can check the class of these individual elements. And we can see that the first one, A, is character, while the last one, 0 plus 4i, is complex. Similarly, I can investigate the length of a list. And in this case, it tells me that we have the four elements. We can, sometimes we might want to convert from a vector to a list, or coerce from a vector to a list. So once again, let's produce a cool kids vector with 4 numbers. If I look at the class of cool kids as numeric, and it's a numeric vector. Now I want to turn it into a list. I can use as list on my cool kids. And you can see that now it returns it with the list notation. Additionally, we can name the individual elements of a list if needed. So these are our list at the moment, cooler kids. And for some obscure reason, I might want to call the element that have characters as characters. I might want to name the elements according to their data type. So I can create my list names object, which is going to be a vector, a character vector with my list name. The first is character, then integer, then decimal. Hello, I'm giving a presentation, sorry. Thanks. And complex. So I have my vector of list names, and now I can use that to assign names to my list with the names function. For kids. And now if I look at fuller kids, you can see that each one of the elements is named according to the name that I provided. So the one with characters, character, integer, and so on. And now if I want, I can access elements within that list based on their name with the $sign notation and then name. I might have gone a bit faster that, so I'm gonna stop for a second and use this time to see if I have forgotten anything, or if anybody has questions about lists. There's more messages in the chat. Okay, I hear crickets. So I might move on to the next data structure, which is data frame, which is probably the data structure that makes R so it's pretty fundamental to R, and it's kind of an expanded list with a particular limitation in that the elements within our data frame list all need to be of the same length. So to better explain that, let's first do one last example for a list with elements in that list of different length. So my first element is going to be cool kids names. I'm not sure if I'm doing this right. So, and cool kids names like Lorenzo or Legana. And then we might have cool kids hair colors, and there's only one good cool kid hair color, which is bold. And I made now a list with two elements. One with these elements were already named. So here I'm assigning the name to the element, and here I'm actually producing the element in the list. So if we now look at our cooler kids, we can see that we have the first name element of the list called cool kids name, and we have two elements within, and then we have the cool kids hair color, and we only have one. This is not possible for data frames. All of our columns and rows need to have the same length. So let's produce our data frame first. Once again, here, let's do it without the names first. So in a data frame, I'm gonna have one column with values from 1 to 5 with the notation that we used before. And then column with sequence of values from 1 to 10. in step of 2. What did I do wrong? This, yes, okay. Seek, if you're unfamiliar with it, seek is a function that makes a sequence of numbers from 1 to 10 in a step of 2. So here you can see that it skips every second number and does 1, 3, 5, 7, 9. Our cool DF data frame now has 2 columns with awful column names and with the values that we provided. The first one going from 1 to 5 and the second one only having uneven numbers between 1 and 10. To make our data frame a bit better, we can provide column names. So the first one will be numbers equals and then the sequence, and the next one will be uneven numbers. And if we now look at our full data frame, we can see that it has beautiful column names. And there's quite a few functions that we can use with data frames to investigate them and work with them and so on. And before I forget them all, I'll copy paste them and we can go through them one by one. And to make this a bit more relevant, so I don't type this now. To make this a bit more relevant, let's make our data frame bigger. So instead of from 1 to 5, let's do from 1 to 50. And then from 1 to 100. Oh, just to prove the point that data frames need to be of the same length. If here I did, we know that 1 to 50 makes 50 numbers. And we can check that with the length function. And we know then we want to have another vector to be the second column in our data frame of length 50. If I just had set from 1 to 50 in a step of 2, I will have way less number, and in particular, I will have 25 numbers as can be checked like this. If I try this now, it will probably return me an error. No, it doesn't. What does it do instead? It fills the remaining positions with the same numbers again. So yeah, cautionary story, don't make sure that you make your data frames with even numbers, or it will usually fill in the gap. I think what it does mostly is fill in the gaps. If I'm using seek, just by replacing, running seek again, if I gave it I think a character vector of 25, it might have filled it with an ace. So now we have our data frame with 2 columns and 50 rows. I know that, but what if I wanted to find out the dimensions? I can use dim just like for the matrix, and you can say it tells me how many columns, how many rows there are, and how many columns. But it's a very big data frame. And before I start with my analysis, I might want to check that the data is looking good, for instance, by using the head function and seeing just the first few columns in a way that's doesn't clog my console. And head will return usually the first 6 rows of your data frame, unless you specify otherwise. So maybe I want to see the first 10 rows, and I can adjust that with the end parameter. I can see a lot of comments in the chat, so I'm quickly going to chat what you all are saying.
We were just messing around.
Oh, okay. Sorry, I saw 12 messages and I thought I did some awful mistakes or forgot something very important. Thanks, Kevin, for the summaries, by the way. Complementary to head, I might use tail to check at the tail or the end of my data frame. And this will return the last 6 rows of my data frame. And just like head, you can adjust it. Maybe I want to look only the last one. we saw how dim works, just like for the matrix, it returns as the dimension, as in how wide and how long is my data frame, as in how many rows and how many columns. Or I might be interested in only the number of rows. For instance, I find myself using this a lot when I'm checking how many SNP there are in my data set, which are usually represented in a data frame. So I might do row, and it might tell me I have only 50 SNPs, so my power of addressing biological signals will be pretty poor. I cannot similarly check how many columns I have with the end column function, and use Legana's and Jacob's favorite function structure. And here you see where I think here is where like structure becomes for me more useful, and I agree with Legana and Jacob. It starts returning very detailed but not overwhelming description of your data set. It's telling me that is and there's a lot of information here. It tells you the class of your data structure, in this case, the data frame. It tells me I have 50 observations or 50 rows for 2 variables or 2 columns. And it tells me the name of my columns, some numbers and uneven numbers. It tells me the data type within those columns. The first one is an integer and the second one is a numerical. And shows me the first 10 rows. And here you can see in what way data frames and lists are similar, as just like we did for named list, we can call individual columns of our data frames with the $sign notation, and then the name of the column. I'll put this up. Maybe it's a bit easier to see. This is my data frame, $sign, and the column. Alternatively, if you do not have names or don't want to work by names, you can inspect data frames by indexing them by either row or column or both. So for instance, if I do 1, comma, and I run this, it returns me only the first row. While if I do comma 1, it returns the first column. So basically on the left side of the comma, we'll have what, sorry, this, what rows you want, and then the comma, and then what column you want. And you can use this together to, for instance, extract a single value. So if I do 1 and 1, it's going to return the first row and the first column, which if we look in our data frame, first row, first column is a 1, and it returns a 1. If I want to extract the 5 here, I'll then need the third row and the second column. So I'll change these to 3 and 2, and you can see that it returns the 5. You can also use the same notation that we used before to do sequences of numbers to retain only a sequence of rows. For instance, rows from 1 to 3. And you can see that now we have the rows from 1 to 3. Similarly, as for the list, our data frames can have names, and we can extract it with the names function. And in this case, it's telling us the names of columns. If we want to be a bit more explicit, we can tell him exactly that we're referring to column names with the column names function. Now, at the moment, our data frame, you can see it has, let's do head, to structure, yeah. You can see that at the moment we have two columns, one with integer data type and one with numerical data type. So this is a reiteration that data frames, just like list, can contain different data types within each across columns. So each column is going to have the same data type, but two different columns can have different data types. To make this more obvious, let's make a new data frame. For names, this time we're going to have a character column with full names. Sorry, misspelled. And then a column with the best numbers, which we all agree are 4, 7, and 9. Best numbers within 1 and 10. And if you now look at the structure of our data frame, we can see we have one column with character data type, which is once again denoted by the double quote, and one column with numerical data type. If, just like for vectors before, if instead of Legana here, I add a number, a numeric data type, or an integer data type, and I produce this data frame and then inspect it, you can see that 4 has now been turned into a character as well. And that's the output you'll have anytime. I think if you include integers in a vector that already has characters, they'll all be first to characters. What is the chat saying? Nothing for now. And I love supply and apply functions. Without the need to understand. You need to understand? Maybe. So now let's say we want to apply the class function to each of the columns in our data frame to see what class the different columns are. We can use supply, and we can see that it returns character for full names and numeric for best number. This is a small data frame, so the str function does the job much better and simpler. But for big data frames, it might be useful. We have 8 minutes. Oh, sorry, and I'll be completely honest with you, I have not had time to prepare for the factor section because I remembered about this presentation 10 minutes before it started. So I might leave this 8 minutes for questions, if anybody has a conversation about what we discussed today and any input you guys might have or things I forgot. You can hear the crickets.
Those would be mine, sorry. I breathe in for my lizards.
Yes, that is a good question, Jacob. That I do not have an answer to.
Next time, man.
Factors like I'm sure Jacob probably knows what a factor is. He's just trying to incite discussion. But factors like a character string, but there's also an underlying levels to it. So like there's some order to the character string intrinsically. So it's really good for when you're trying to plot like multiple populations, and maybe you've got like populations in some kind of order that you want. You want them to keep in that order. Use a factor to basically make the plot keep it in that order usually. You can trick R kind of into a certain order. Yeah, that's how I think of factors at least. It's like a character string, but with an underlying order to it.
Let's give an example of that and what Kevin means. I'll be done in 2 minutes. Sorry, I'm giving this presentation from the lab. Let's say we have our first character vector, and then we have these 4 numbers in our data frame, and we want to plot what have I done? Oh,
Lorenzo's playing a dangerous game of plotting on the fly.
No, I'm there. Okay.
Nice.
We do have a plot 20 days later. So I might have this plot, and I do not like the order in which the names are. At the moment, they're in alphabetic order, but to me, the alphabetic order might not mean anything. I might want to plot them by any other order. So I can coerce my column that includes the name to a factor with the as factor function. And there's one of these functions for any of the data types you want to coerce to, like as integer, as character, and so on. So first I coerce it to factor. And if I look at the structure of my data frame, I can see that full names is now a factor with 3 levels. And it also tells me how it's interpreting the order of this level here. That's a bit unclear, but we can be a bit more straightforward by giving it the order that we want ourselves. Which I do not remember how to do. Maybe I do. Yes, I do. With the levels option. So I want Legana to be first. I'm going to put it first, and then Jacob, and then Kevin. Now, if I go back to my flow, it's not going to work. No joking. We can see that I forced this character to a factor, convert it to a factor, and then I gave it the levels in the order that I want, like Legana first, Jacob second, and Kevin first, instead of how I originally interpreted them as Jacob, Kevin, Legana, which was alphabet. I think that's what Kevin was referring to, and that's what factors can be useful for. Okay, I think it's 2 minutes to 12, and I think I did my best to cover most topics today.
Super good, Lorenzo. Thank you.
Yeah, it's awesome. That's like a lot bigger one than I realized, like how much you have to do in it. So you got through it all, which is good.
Yeah, thank you. That was really good.
Yeah, I'm sorry if my terminology was not very accurate at some stages. I'm very informally trained in R, as in Google and asking. So sometimes my terminology is not as accurate as it could be. But hopefully it was clear.
It was good. It made sense.
Okay.
Nobody can do what time except for what time.
What about some of the newer R users?